Okay, so yeah, so the title of this talk is Basics on Motivic Integration, and my goal here is a little bit modest, and the idea is to introduce some very basic stuff on Motivic integration, mainly the notion of Motivic volume, and also to compute some simple integrals in this setting. Okay, so the plan of the talk will be as follows. So first, I will introduce the so-called Motivic ring, which is the ring in which Motivic measures and integrals takes values. And then I will introduce the formal arc space of a variety, of an algebraic variety. And this is going to be the base for the base space, let's say, for the purposes of Motivic integration. Okay, so closely related to this, to point 2 is point 3, which is I will explain a little bit about what kind of subsets of the arc space are considered to be measurable and in what sense. And then finally, I will compute some the most elementary example of a Motivic integral for the so-called order contact functions along a divisor of x, or along a divisor of x. Okay, so this is the plan. So let me start with by saying some things about the Motivic ring. So the idea is that the Motivic ring, this ring in which Motivic volumes lives, is or can be constructed out of the Grothendieck ring of varieties, of algebraic varieties, by a process first by taking a localization of that ring, and then by completing this ring with respect to some norm. Okay, so let me just recall briefly what is the Grothendieck ring of varieties, and for that purpose, let me fix an algebraically closed field K, which you can think, of course, as the complex numbers if you want. But in any case, the Grothendieck ring of varieties, this K0 of the category of varieties over K, is defined as the free abelian group generated by isomorphism classes of varieties over K, and we impose the following kind of relations. So whenever we have a closed subset of X, then the class of X can be split out in two terms. One of them is the class of the subvariety X, and the other term is just the part of X which we obtain by qutting along this Y. Okay, so this is the Grothendieck ring of varieties, and we can define, moreover, a product on this set. So this is an abelian group. It's a free abelian group. Yeah.
Sorry, I think you don't have to zoom in. I think it's clearly, we can clearly see it even if you don't zoom in with this.
Okay.
Right.
Thank you.
Yeah.
Okay. So yeah. So this is an abelian group, but we can also introduce a multiplication on this set by taking the product of the class of some variety X and the class of some variety Y, just by taking the fiber product over K of these two varieties. Okay, so in particular, the unit of this ring, this is a unital ring, and the unity in this ring will be just the class of a point. Okay, so let me see a simple example. So, for example, suppose that we start with the projective space of dimension n over K, and remember that we have a stratification of that space by affine spaces. So we can obtain Pn by starting with a point, and then we can add a line and then a plane, etc., up to an affine space of dimension n. Okay, so this is a stratification by closed subvarieties of Pn, and because of that, we can split the class of Pn as the sum of, as a sort of geometric series. So you have you can define the class. Well, the class of the affine line is sometimes called as the Lefschetz motif, and this is an element in the group of group of varieties, and the classes of these of these affine spaces can be written as the product as a power of the Lefschetz motif, and we can obtain such kind of the composition for the class of the projective space. Okay, so let me point out a remark. We don't impose any restriction whatsoever in the varieties in order to define the Grothendieck of varieties. They are also finite type schemes, let's say reduced schemes over K, but we can generate this Grothendieck of varieties by means of smooth varieties. And this is just because every variety has an stratification by smooth subvarieties, and then we can start just with smooth ones. Moreover, it is a theorem of Bittner that if we start with those smooth varieties, then we can reconstruct the Grothendieck of varieties just by imposing this kind of relations between its elements. So we can take a blow up of some variety X along a smooth device, a smooth subvariety, and we can impose just this kind of relations involving the blow up, the exceptional divisor, and the center of the blowing up. Okay, so let's see how we can write the class of some variety Y whenever we know that that variety lives above another variety X, but in such a way that that it is the total space of a trivial bundle over X. So suppose that we have a map F which goes from this Y to X, and suppose as well that X has an stratification by locally finite subsets of X in such a way that when we restrict this F onto each strata, each Xi, then the map looks like as a trivial fibration with fiber C. So we have this. If we have this kind of stratification of X, then we can compute the class of Y in the Motivic ring, and this turns out to be just the product of the base and the class of the base times the class of the fiber. So this observation will be useful later in order to compute some integrals. But now, so this is the Grothendieck ring of varieties, and in this ring there is a filtration, so-called dimensional filtration, and it is by means of this filtration by dimension that we can get a completed version of the Grothendieck ring. I think we can take a completion with respect to the dimensional filtration. So the idea is that any element in the Grothendieck ring, if we start with an element, let me call this tau. So we have this element tau here in the Grothendieck ring, and any such element can be written down as a formal sum of the classes of some varieties Xi, and this A sub I belongs to the integer. So we can always split just by definition. Sorry, this is set, and we can split any element by in that form as a formal sum of classes of varieties, and we can ask of the infimum of the dimensions of such a splitting of the class tau. So we can take the infimum of the dimension. So here is the dimension of each Xi. We are supposing that each Xi have the same dimension. And if we take the infimum, then this is by definition the dimension of the corresponding class in the Grothendieck ring. Okay. Moreover, we also define the dimension of the class of the empty variety just as minus infinity, and this defines a map from the Grothendieck-ring of varieties onto the non-negative integers union with this minus infinity. So this dimension function has some nice properties. In particular, the dimension of the product of two classes is always less than the product of the dimensions of each one independently. And we also have this inequality, which tells us that the dimension of the sum of two classes is less than the supremum or the maximum of the dimensions of each class, which appears in the sum. So another way to see this is that we can define a new function, delta, by taking the exponential of the dimension. And this delta defines, in fact, a non-Archimedean norm on the Grothendieck-ring of variety. So we have this non-Archimedean norm, and out of this norm, we can take the completion of the Grothendieck-ring, and we can obtain a complete norm ring in that way. Okay, so now we are almost ready to define what is the Motivic ring. But first, we need to take a localization of that thing, and here we just take the formal inverse of the Lefschetz motive. So by definition, the Motivic ring is obtained from the Grothendieck-ring of varieties just by inverting this L there. And the dimensional filtration can also be extended to this localization. So we can define the dimension of the inverse of the Lefschetz motive just as -1, and now we have a kind of virtual dimensions for the elements of the Motivic ring, which can be positive or negative or minus infinity, if sometimes. Okay, so just as above, as here, we can also define a non-Archimedean norm in the Motivic ring by taking the exponential of the dimension function. And in this way, we obtain a norm, a non-Archimedean one in Mk, and we can just take the completion of this ring. So by definition, this thing here is just the Grothendieck-ring of varieties localized at the Lefschetz motive and then taking the completion with respect to the dimensional filtration. Okay, so let's see how does some computations in this completed ring looks like. So for instance, first let me just point out that convergence in this ring is very simple. So the idea is that a sequence of elements in the Motivic ring converge to 0 if and only if the dimensions of each of its elements goes to -infinity as t goes to infinity. So, and since we are in a non-Archimedean setting, then a series will converge if and only if the norms of the elements of the series goes to 0. Okay, so for instance, we can compute, or we can try to get a bound for the dimension of the geometric series corresponding to L minus M. So we can fix a power M, and we can take the geometric series corresponding to this guy here, and the dimension of this term, of this difference, is just it is not so hard to see from the basic properties of the dimensional norm, or the notion of dimension or virtual dimension, that the dimension of this term here is bounded by n+1 times the dimension of something. Okay, so in any case, this term here is negative and this is positive, and it turns out then that the limit must be -infinity, or in other words, we can obtain this kind of of geometric series as in usual analysis. Okay. Any question? Do you have any question?
So,
okay. Yeah.
Formally, you should first prove that this element 1 minus L to the minus M is invertible, right?
Yeah. Yeah, in fact, in most computations, this it will appear this kind of geometric series with respect to the inverse of the Lefschetz motive, as we are going to see at the end of the talk. Okay. So now, so this goes for the first part. So we define the completion of the Motivic ring of varieties, and then let me just introduce the base space in which Motivic measures takes place, which is the space of formal arcs of a variety. Okay, so let me start with the variety X, and here I'm assuming that X is smooth. This can also be done when X is singular, but the theory requires some modification in order to this works nicely. So this is the most basic case when X is smooth, but in any case, this can be extended for some types of singular varieties. In particular, I'm interested mostly in varieties which have this kind of orbifold singularities. Or for these kind of singularities, this theory works nicely. Okay, so so let me start with this smooth variety X, and by definition, a formal arc or a truncated or n-jet formal arc on X is simply given by by a map from the spectrum of this guy here. So this is it's kind of a formal n infinitesimal neighborhood or something like that, and we define an n-jet or a formal n arc on X simply as a map from this kind of formal disk, the n, given by the spectrum of this guy here. And it turns out that we can define a scheme out of these truncated arcs in such a way that the points of such space, so this Ln will be a scheme such that its k points, so these are the k points of this scheme Ln of X, will be given by the set of n truncated arcs. So these are by definition the jet spaces of X, and yeah. So in other words, we can start with this functor here. So we have this functor like this, and it is a theorem or a result of Greenberg that this functor is representable, and it is representable by the arc space. Okay, so note that we have for any n we can consider the corresponding canonical projections of these truncated polynomials. So an element here is just a polynomial of degree n minus 1, and this is a polynomial of degree n, and we can just forget the last coefficient or the coefficient in the highest power, and this produces a projection or a truncation map. And out of this truncation map, we can extend this, or we can induce out of this truncation map a map between the corresponding arc spaces. And by composing these truncations, we also can obtain a projection from the space of truncated n arcs onto the base space X. Okay, so for instance, if we consider just the one jets, these correspond exactly with the notion of a tangent direction. and the space of widgets is nothing but the tangent bundle, and the projection, and this projection given by the truncation map is just the tangent bundle of X. Okay, so for example, if X is smooth, as we are assuming, then the tangent bundle will be smooth as well. And this is true also for higher NZ spaces. So whenever X is smooth, then all the jet spaces are also smooth, and they are schemes of finite type over K, but it seems that they can have they are not reduced in general. Okay, so this, by the way, these arc spaces are much more complicated and much more interesting when X is not smooth, when X can have singularities, because in some way these arc spaces give some information about the singularities of X. I think that this is not so well understood yet, but it's a kind of classical, or this is the original motivation for one of the original motivations for introducing these arc spaces in algebraic geometry. Okay, so let's see an example. So consider or take the affine M space. So we consider the space, the affine space of dimension M. This is just the spectrum of the corresponding polynomial ring in M variables. And how does the arcs, the formal arcs looks like in this case? So just by definition, an arc, or let's say an N arc on the affine space will be given by a map of K algebras from the ring of polynomial functions in N variables onto this ring of truncated polynomials in one variable T. So this map is completely determined by the values which taken in the generators T1, T2, etc. up to Tn, and each one of these the image of these generators can be written as polynomials of degree n, and the coefficients of these polynomials, which are elements in K, determines completely the arc. And in fact, it turns out that the corresponding arc space of dimension n and the nz space of the affine space is another affine space. And the dimension will be just the product of the original dimension times n plus 1. Okay, moreover, the projection, the canonical projection from the n arc space onto X is a trivial AM bundle. And this turns out to be this kind of affine bundles will be this kind of behavior is also appears in general whenever we have a more complicated variety, not an affine space. Okay, in any case,
Enrique,
yeah.
So sorry, you have this it's an plus 1 bundle, but it should be a tangent bundle for any cross 1, right? So
yeah, I think that this must be times M, right?
Yes,
Like
okay. Yeah,
yeah.
So isn't it A and M?
A and M?
Yeah, I think.
No, because if when n is equal to 1, this is just the tangent bundle, and the
yeah, but this is the so A n plus 1 times M is the total space, and the fiber has a dimension.
Yeah, the dimension of the fiber is just the dimension of X, right? So yeah, you're right. This is just this must be just
Mn.
M. This is just M. Okay.
No, M times N.
No,
right?
no. It's M times N. Yeah.
Yeah.
Thank you. Okay, so this is for the affine space. So in general, whenever we have a smooth variety X, then of dimension M, let's say, the n arg space is a smooth scheme of finite type over K, and the projection, and here I also need to take, I suppose this is just n times M, okay? And we have the projection, when X is smooth, the projection turns out to be a locally trivial bundle with fibers affine spaces of the appropriate dimension. Okay, and this is the projection onto X, but we also have these consecutive projections from n onto n minus 1, and these are also affine bundles of the appropriate dimension. In this case, I think that this is correct. This is AM. This is an AM bundle. Okay. So this kind of behavior is what is the computations that we are going to see heavily relies on this kind of behavior of the for the projections of arc spaces. But well, so now let me introduce a class of subsets of the arc spaces. I will let me just correct this. This is L infinity. L infinity. I think that I don't define what is L infinity in these notes. Okay, yeah. Well, so let me briefly define what is L infinity, and L infinity is just we have these arc spaces for varying n, and we have the corresponding projections by truncation, and we can take the limit of these guys and define the formal arc space. So these are formal arcs on X. This is the limit as n goes to infinity of these Ln's of X, and the K points of, this is the formal arc space, and the K points of this guy are given just by maps from the formal disk onto X. Okay, so this is L infinity. And this is the basis space for Motivic integration, this L infinity. Okay, so now let me describe what kind of, or a class of subsets of L infinity that for which it makes sense to define the notion of Motivic volume. So for this class of subsets, we are going to be able to define an element in the Motivic ring, and we think of this element as a sort of volume of such a subset. Okay, so let me just introduce a definition here. So a subset A of the arc space will be called stable whenever, or if for a big enough number n, the subset which is obtained by taking the projection of, so we have projections like this as well. So from L infinity, we have canonical projections into Ln of X, and we will say that a subset of L infinity is stable if for a big enough n, the projection A sub n of this subset A, which lives here, which belongs to Ln, the space of n truncated arcs, is a constructible subset. So this Ln is a variety. So whenever A sub n, the projection is constructible, and moreover, when the restricted map obtained by the projections from A n plus 1 onto n sorry. So this is just the restriction of the canonical truncation maps. is a bundle of the appropriate dimension, which in this case is just the dimension of X. So if these two things happen, if the projection is constructible and the restriction of the canonical projections are affine bundles, then we're going to say that A is an unstable subset. And this is important because for those subsets of L infinity, we can define the volume of such a subset just as the limit. I put here the limit of this is kind of a normalization. So this factor here, this is just the class in the Motivic ring of AN, which is a constructible subset of a variety. So we have a constructible subset of a variety, and we can define out of this constructible subset a class in the Motivic ring. But we take a sort of normalization for this class by dividing over an appropriate power of the Lefschetz motive. So this is the dimension of X times the dimension in which we are truncating our arcs. So for stable subsets, this is independent of n for n big enough. So we can take we can define this just as a limit in order to avoid ambiguity. And this turns out to be an element in the Motivic ring, which by definition is the Motivic volume of such guy A. Okay, so for instance, for example, when X is smooth, we have a particular type of stable subsets which are let's say more easy to handle, to deal with, which are the so-called cylinder sets. And by definition, a subset of L infinity, so we have here a subset of L infinity, will be called a cylinder set if it is just the if it is obtained as the inverse image by the truncation maps of some constructible subset. So we have a constructible subset of arcs, of n arcs, and the inverse image of such a thing is called a cylinder set. So it turns out that cylinder sets are stable when X is smooth, and this is kind of a generating family of measurable subsets in L infinity. So even if the subsets which will appear in when we compute Motivic integrals are not stable nor measurable in an appropriate sense, then it can always be approximated by cylinder subsets, and we can define the measure just by taking the limit of the corresponding approximation. Okay, now, so this I think that this is kind of the very basic language, at least of this subject. So we have at this point we have a ring in which our measure takes values, and we also have a space, a base space in which the measure takes place, and we also have a class of subsets which in fact turns out to be an algebra of subsets of L infinity, of the space of formal arcs. So now, what about the integrable functions in this setting? So I will not define in general what is the Motivic integral of a measurable function, but I will introduce an important class of functions for which we can define the integral, the Motivic integral for these kind of functions. So, so let me just define what kind of functions I have in mind. And let's begin with a subscheme, let's say, of X. So we have our variety X, which we are assuming to be smooth. And let's take a sub-variety, or we can also think, yeah, let's say that Y is just a sub-variety. So we have this sub-variety of X, and let me just denote the ideal sheaf, which is defining this subvariety by the like this. So we have the ideal shift, which is defining this y, and we can define a sort of order for formal arcs on x along the subvariety y. So the idea is just that, so we can start with an arc. So we have a formal arc on x. So we have this arc, which is a map from the formal disk onto x. And we have this subvariety y, and we can ask what is the contact order of this thing along y. So, for example, we can take the truncation at 0 of this arc, and the truncation is just a point in our variety. So, in order for this order function to be non-zero, we ask for the value of this order function to be different from 0. So, at the end, the order function will be just a function, kind of function, from the space of formal arcs onto the positive integers, maybe with maybe we can also allow an infinite contact order for these things. And the point is that the order of an arc will be bigger than 0 if and only if the arc or the base point of the arc, which is given by the projection or the truncation at 0 at x, is a point which belongs to y. Okay, but we can also think about higher order contact. So this is an incidence relation. We can ask for the base point of formal arc to belong to y, but we can also ask for the higher order, let's say, infinitesimal dimensions to belong to the dimensions corresponding to y. So for example, we can think of the tangent bundles. Let me just think about the tangent bundle of x, and we have the corresponding tangent bundle of y, which lives inside the tangent bundle of x, and we say that the contact order of our arc is bigger than 1 whenever the tangent direction, which determines this arc, so an arc determines a base point and also a direction, a tangent direction, which is the truncation into the first jet space. So this is kind of a tangent direction in x, so this is kind of a tangent direction. And if this tangent direction belong to the tangent directions defined by y, then we just say that the order is bigger than 1. And we can extend this idea in general for higher orders. So we will say that the order, or we define the, we will say that the order of for formal arc is bigger than some positive integer n whenever the truncation at n-1 belongs to, so I think that for tangent directions it must be bigger than 2, right? So for tangent directions, the order needs to be bigger than 1, and for order which are bigger than n, this only happens if the truncation at n-1 belongs to the directions defined by this y inside x. Moreover, if this happens for all orders, then of course we just this just means that the arc in fact belongs to the it is just an what I want to say is that if the order is infinity, this is just another way to say that the arc belongs in fact to the subset of formal arcs on y. So the formal arcs on y lives as a part of the formal arcs of x, and whenever this happens, then we say that the corresponding order is infinity. Okay, so this is the idea for the contact order function, and this function turns out to be a measurable function in the sense that if we take so let's fix an integer n, we can fix an integer n, and we can consider the collection of all arcs which has order bigger or equal to n, and this is just the inverse image through the truncation map at n-1 of the arcs of those arcs which are induced by y inside X. So this, since everything is, well, since X is smooth here, this implies, or this means that these subsets here are in fact cylinder subsets. So they are measurable in the sense of Motivic integration, and we can assign to that subset a Motivic volume in the Motivic ring. Okay, so we have this function, and this function is a measurable function in that sense. However, we need also to consider which is or if the inverse image of at infinity is a measurable subset or not. But in this case, the subset of arcs which belong to the arcs of y, so we have this L infinity of y, which lives inside L infinity of x, and this subset is not a cylinder, but it can always be approximated by cylinder subsets. So it is measurable in an appropriate sense. When you develop appropriately this theory, then this subset turns out to be also a measurable subset. Okay, so in fact, this subset is kind of a measured zero subset, at least whenever y is a nowhere dense subvariety. So if you have a closed nowhere dense subset of x, the corresponding arc space inside the arc space of x has measure 0. So this is the measure with respect to the ambient space. So inside the ambient arc space, the arc space of y has measure 0. Okay. So now the kind of functions that we are going to consider to define the integral, the Motivic integral, will be like this. So this function is constructed out of the order function, and it assigned to every arc. So we have formal arc on X, and we can map this arc into a class in the Motivic ring given as a power of the inverse of Lefschetz motive, just by taking the order of that arc, and this lives here. Okay, so this is a function from the arc space into the Motivic ring, and this function, just because of what I just said, is a measurable function, and then we can define the integral of such function. Okay, and how can we define the integral of this function? Well, we can just take level subsets, so we can fix an order. So by definition, the integral of our function with respect to the Motivic measure in X will be given just as a series of this kind. So here we fix the order. So these correspond to arcs of order n. So these arcs lives in X, in L infinity of X, and we take the collection of the measure, the volume of the collection of those arcs which have that order, has order n exactly. So by definition, this is the, or we can define the Motivic integral. So we can define this Motivic integral by means of this kind of series. Okay. So now, let me just remark here that the dimension, this makes sense because, so this is a series in the Motivic ring, and we are saying that this series converge in the Motivic ring. So this, the elements of this series must converge individually to infinity as n goes to infinity. But in fact, the dimension, just as in the example at the beginning, you can get a bound for this virtual dimension. In this case, it is a virtual dimension because we need to take into account negative dimensions for this L to the minus n. But this in fact converges to minus infinity, which means that the elements of the series goes to 0 as n goes to infinity. So this series, in fact, is a convergent series in the Motivic ring. Okay. Moreover, here we are assuming that y is nowhere dense, but in that case, when y is nowhere dense closed subset of x, then the volume of the collection of arcs which has order infinite order is 0. So we strictly speaking, we need to add here something which correspond to the measure of this thing here. But since we have things of measure 0, we don't need to have nothing here at the end of this. So we can define the Motivic integral just like this. Okay, so let me end by showing or by computing some very, very simple examples. So the trivial example will be when y is just the empty subset. And for the empty subset, we have, well, we don't have nothing except for the trivial condition of those arcs which lie or not lie in the empty subset. So this series reduced to just to the first term. But well, in this case, this just corresponds to the Motivic volume of x. So the Motivic volume for the whole space turns out to be just equal to the class of x in the Motivic ring when x is smooth. So when x is smooth, the Motivic volume of x turns out to be just the class of x, like this. Okay. So this is the first and trivial example of this Motivic integral, the Motivic integral of this kind of order functions. And let me now see a little bit more interesting example. So so suppose now that we have an non-empty subvariety, but let me assume that y is smooth. So we have two smooth varieties. We have the smooth variety x, and we have a smooth subvariety y inside x. So in this case, the order we can compute explicitly, which is the inverse, the collection of arcs which has order n, and this is an arc will the order of an arc will be equal to n if and only if the truncation at n-1 belongs to the arc space of y, and we need to subtract those arcs such that it also lies in Ln of y. So this thing, we can extract the part of those arcs. So these are the arcs which has order greater or equal to n, and these are the arcs which has order greater or equal to n+1. And if we subtract these two things, well, we just obtain the collection of those arcs which has order exactly n. So so let me denote the dimension of x by m, and from this equality we can compute the Motivic volume of the subset of arcs of order n. And in this case, I think that this yeah. So we have two stable subsets, and we need to subtract the Motivic volume of one and the other. So we have the Motivic volume of the corresponding arc space will be given just by the class of the arc space normalized by an appropriate power I think that this is also need to be modified a little bit because of the mistake at the beginning. But in any case, we can compute explicitly what is the Motivic volume of this thing, and this is just a product of the class in the Motivic ring of the arc space normalized appropriately, and the same goes for the second term here. So at the end, the point is that since everything is smooth here, since Y is a smooth subvariety, then each one of these arc spaces, Ln minus 1 over Y, if we take the truncation map, then this map is a locally trivial affine bundle for an appropriate affine space here. So we have a sort of locally trivial bundle, and then by the observation at the beginning of the talk, we can compute explicitly what is the class in the Motivic ring of the arc space of Y. And this turns out to be just the class of the fiber times the class of the base. Okay, so we have this, we can express the Motivic volumes in terms which just involve the class of the subvariety Y and the appropriate powers of the Lefschetz motive here. Okay, so this is where the local this property of being a affine bundle is used explicitly in this kind of calculations in order to compute these integrals, and we can just I think that this is yeah, I need to correct this part here at the end because of the dimensions that I write wrongly here. But in any case, at the end, when we use this splitting, the Motivic integral turns out to be just it can be obtained by computing an appropriate geometric series. So the geometric series here plays a very important role, and we can obtain expressions like this. So yeah, so I think that I can stop here. Since yeah, I will stop here. Thank you.
Thank you. Are there any questions? Enrique, so how do you get this x minus y there? Is it because of the order 0?
Yeah, this term is it corresponds with n equal to 0. Yeah.
Yes, and all of them are like bundles over y, so then you can use just the class of y.
So yeah, the point here is that the Motivic volumes of each of these subsets given by the order function can be computed in terms of the Lefschetz motif, powers of the Lefschetz motif, and classes of the arc spaces. So this guy here is the Motivic volume of this thing here, and this is the corresponding Motivic volume, which is given by a normalization of the class of the arc space, and then we can use this property that the projection is an affine bundle in order to split this thing as a product of the class of Y and the class of some affine space.
Mm-hmm.
Hi, Eric. So you said the arc space has a deep relation with singularity of varieties. Do you know any reference about this?
Yeah, I can send you. There is a paper, a survey paper by Tommaso de Fernex, in which he explained the well, he explained some things about the relation between singularity theory and arc spaces.
Excuse me, by whom?
Tommaso de Fernex.
Okay.
Tommaso, I don't remember how to.
Tommaso
probably. And I think that the title is something like the arc space of a variety.
Okay, thank you.
Yeah, if not, let's thank Enrique for a very nice talk. Yeah, and hopefully we will see each other next week in person.